All right. Morning. So we're going to be picking up today where we left off with 3D graphics and processing. We're going to be finishing off with that today, and then moving into a bit of hardware prototyping. So for you guys' next assignment, Mark and I are just going to have a meeting about this afternoon, just to sort of lock down the last of it, and then we'll put it on Learn this afternoon. But basically, we're going to try and have some assignment for you guys, which will combine some bit of processing, some graphics, and some Arduino-based stuff as well. So you'll be doing some software and some hardware prototyping, and you have a couple of weeks. So I know we haven't touched on Arduinos yet, but by this time next week, you should have a fair understanding, and we'll get you some kits that you guys can take and have a play with as well. Anyway, so last week we looked at graphics programming and processing. We started with 2D, and then we moved into 3D. We looked at transformations, and then we looked at various objects you can draw. Then we looked at things like cameras, different viewing projections, and so on and so forth. So perspective, orthographic, so on and so forth. Hopefully you guys might have had a bit of a chance to sort of open up some of those examples and have a play with stuff. If not, when you get a chance, you should have a look. It makes a lot more sense when you sort of play around with it yourself. So we're going to move on, just cover the last sort of few bits and pieces today on graphics and processing. So starting with color. So seems fairly fundamental. You tell an object you want it to be a specific color, and it's that color. However, when you start talking about 3D geometry and things like lighting and shading, it gets a little bit more complicated. So the surface color at a point on an illuminated object depends on the characteristics of the light. So if we use this teapot, for example, we're looking at this one specific pixel here. The color which you're going to see is going to depend on the light or the lights in the scene, because there could be more than one. So each light can have its own color. So obviously in here the lights are sort of a white color, but you can have obviously red lights, blue lights, whatever else. Their position, so depending on how far away and what type of light it is, will depend on how much it's lit up. If it's actually light characteristics includes type as well, because in computer graphics we can have spotlights, we can have directional lights, we can have point lights, so on and so forth. So if it's a directional light or something which has the idea of like a torch which shines in something rather than a light bulb which sort of shines everywhere, the direction can matter, because obviously if we have a torch and we're not actually pointing it at the object we want to light up, it's not going to light up. So yeah, the color depends on the light characteristics, the geometry of the object, so its orientation and the position with respect to the viewer. So we have various lighting things. We have diffuse lighting, we have ambient lighting, and we have specular lighting. So the orientation matters, as does the view, because if you look at things like, for example, this projector here, it's got quite a shiny surface, and if I'm looking sort of directly at it, it looks black, but then as I start sort of moving my head, it becomes more and more reflective, and we have these sorts of properties with lit objects in 3D, in the 3D environment as well. So, depending on your orientation, the surface orientation and the light source's orientation, it might be, this sort of yellow color, but then if the object is here and the light is here and I'm looking at the object like that, it actually acts quite reflective, and so we'll get what's known as specular highlights, where it appears really bright and it's almost reflecting the light like a mirror. Then there's also the material properties of the object, so coefficients of reflection, you can make things more or less reflective, so you could have a very matte teapot like this one here. You could have like a really shiny one, like it was made out of chrome or something, so that it reflects the light. Then there's also what illumination model you use, so there's various different mathematical models which try and mimic different types of lighting, and they may be more or less accurate, which means they may be faster or slower to run. And the shading model as well, so there's a bunch of different shading models which again do the same thing. Some of them are more accurate but take longer to process. Some of them are faster but look less realistic. It depends what you want to do. Do you want to make a photorealistic picture, or do you want to just have a game which looks nice but runs at 60 frames a second? So the interaction of light with the material color, so this is sort of the first thing, light characteristics. If we look at a very simple illumination model where the color that we see, so the reflected color off the object, is equal to the light color times the material color. If we have this example here, so we have our purple teapot, and we shine, so it's magenta, its color is 1011, so If this is RGB, this is red, green, and blue, and this is the alpha color. So it's not quite so relevant when we're talking about lighting, but if you're talking about transparency or whatever, alpha becomes important. But often you'll see it written with the alpha, and the alpha is just set to 1. So this is 255 red, 0 green, 255 blue, which is purple for our object. We have a cyan colored light, so 0 red, 255 green, or 1, because these are clamped from 0 to 1 rather than 0 to 255. So 0, 255, 255, or 1, 1. So we end up with a sort of light blue light shining on it. And if in our simple illumination model, we basically multiply the two of these together. So we multiply 0 with 1, which is 0, 1 with 0, which is 0, and 1 with 1, which is 1. And we end up with our reflection of 0, 0, 1, 0. So we have a purple teapot, we have a cyan or sort of light bluey, greeny coloured light shining in, and what we actually see is a blue teapot, which kind of seems a little bit counterintuitive, but it's kind of how it works in the real world, except in the real world everything's a lot more complicated. So you have lights reflecting off various objects and everything, so you know, it sort of comes out somewhere between purple and blue and cyan in real life. So yeah, looking at another example, as I mentioned before, there's 3 different types of lighting, which is typically represented in the 3D world. There's the ambient lighting. So ambient lighting is sort of the zero state or the default state of lighting. So in here, if we switched off all the lights, the ambient lighting would sort of be the light coming in through the windows from the sun. So there's no, you know, obviously the sun is the source of light, but we can't really see it from where we are, so we don't have to worry about its reflection or anything like that. So it'll just sort of be that ambient level of light in the room. So if your ambient level of light is black and you have no light source in your scene, you won't see anything. Like the screen will just be full of black pixels. If you have your ambient light set as anything else, everything else, if there's no lights in the scene, will be that color. So, you know, for example, in this one here, we have the ambient light set at 0.2, 0.2, 0.2. So everything in the scene, every object in the scene will have, at the very least, a slight grayness to them. They'll pick up a little bit of this ambient light and sort of show it. Then we have the diffuse light. So diffuse light is sort of, for a light source, is what the light, when it hits an object, but it's not hitting it at a specular reflection. So, you know, the sort of, when we look at the light source perhaps on something like this, which is more of a matte color, what we're seeing there is more or less the diffuse light. So it's the light which is reflected off other surfaces and all that sort of stuff, and it's then reflected off our object and back into our eyes. So we can sort of see it. We can see, you know, the diffuse light is causing this to look grey because, and you know, this is quite a matte surface, so it's mainly reflecting the diffuse light, whereas this, being that it's quite shiny, is reflecting a lot of specular light. So the diffuse light is sort of, you know, if you had a light source and say we put some filters over these lights, so that they weren't directly shining on things, they were sort of had to reflect off the walls and stuff. That's more what we're talking about when we talk about diffuse light. So ambient light is the light which will be coming in from the sun, from, in this case, from outside. Diffuse light, if you'd imagine we put some bed sheets or something over the lights, would be that sort of stuff after it's scattered, reflected off the environment, and so on and so forth. And then the specular highlights is like the light which is being reflected off the object into our eyes. So, you know, with this shiny projector, if you tilt your head, you can actually see the reflection of the light bouncing off it. So typically, like, the specular highlights of an object depend on its surface, what's known as a surface normal. So the surface normal is a vector perpendicular to the flat side of the object, so the face of the object. So in this case, the surface normal would point directly out. And I mean, I don't know how much you guys know about geometry and stuff like that, but specular light is basically when we have the angle of incidence equals angle of reflection. So when we have a surface, and here's its surface normal, a light ray coming in will hit that and it'll bounce off at the same angle relative to the surface normal. So if it comes in at, you know, 30 degrees, it'll come out at 30 degrees relative to the surface normal. So if I'm looking like that and I have the light there, the light's coming in at that direction, it's going to reflect more or less out into my eyes, and that's what we're talking about when we talk about specular highlights. We're basically acting as if this surface is a mirror reflecting the light of the light. So here it's reflecting off there and straight into my eyes, and that's the specular, what we talk about when we talk about specular lighting, is basically that. where an object is at such an angle that the light off the light source is reflecting into our eyes. And you can actually see that. So even with this, which is quite matte, when I hold it up like that, you know, it suddenly gets a lot brighter because a lot more of the light from the light source is reflecting into my eyes. So those are the three characteristics of our light source. And you'll see when you're creating light sources or whatever in 3D graphics, so in processing, in OpenGL or whatever, you can define the ambient light that is emitted from a light source, its diffuse light, and its specular light. And they can be three completely different things, which isn't really a good sort of approximation of the real world, but it allows you to do some interesting things. With a single light source, you can do sort of what would take multiple light sources in the real world, because obviously in the real world, we really only have, like, these lights are just emitting one color, whereas we can sort of say, oh, well, we'll say this light emits an ambient color, so objects it's not shining on will be lit up with this color. Diffuse light, so objects that it's shining on but it's not reflecting directly into our eyes, will be this color, and specular highlights can be this color. So with this example here, we see we have the same example. So we have our magenta teapot. So this is the color of the teapot. And this is actually what we see. So this is a single light reflecting on this teapot. Areas which are not lit by the light. So you can tell the light source, if this is our teapot here, the light source is sort of shining in this way. So it's off to that diagonal. So parts of the teapot which aren't directly lit by the light get combined with our ambient light. So this is purple, and purple multiplied by grey is grey. And then we have our diffuse. So this is using that cyan color we had before. So when we saw that before, magenta times cyan is blue. So all parts of our light, all parts of our object which are lit using the diffuse part of our light, so they're not reflecting directly back into our eyes, come out blue. And then the specular light, or specular properties of this light, is yellow. And if we multiply this one here, so this is yellow 101 with our, down here, 110, which is our specular quality of our light, with 101, we can see the red 1 and 1 times out to be 1, 0 and 1 is 0, 0, 1 and 0, 0, so we end up with 1, 0, 0, which is obviously red, so we end up with this reddy sort of tinge in the specular highlight. So even though, I mean, hasn't multiplied out perfectly, because that's only going to be the value for specific parts of the teapot where it's directly reflecting it, but there is a more reddish tinge there than what it was purple before. So yeah, we've basically created a light bulb which has three different sort of colors emitting on it, depending on what part of the surface it hits. So it's a little bit sort of confusing, but do you guys sort of follow, hopefully? So we'll look at an example of this anyway, and hopefully it'll clear things up a little bit. Certainly lighting is, I personally think, one of the hardest things about 3D sort of geometry. I've managed to get my head around 3D transformations and stuff, you know, having worked with them for enough times, but lighting is something that it always takes me a few attempts before I finally get the effect that I'm looking for. So I'll just turn the lights off because this is kind of hard to see in this example. So where were we? This one here, and we're looking at, in the examples, basics. So again, there's an entire subfolder in here for lights that you can look at. But let's have a look at Spotlight to begin with. So this is, you know, a sort of example we've got going on here. So this one actually has, I think, 3 lights in it. Yeah, so it has a directional light and 2 spotlights. So the directional light, and we'll look at these in a bit more detail in a minute. A directional light is basically a light source where we define, I think, the XYZ position. So we say, here is where this light is in space, and then we also say which direction it's pointing. So you can think of this as like a floodlight sort of thing when, you know, you go to the airport or circus or whatever, and they have those huge big floodlights which sort of, you know, they shine up into the sky. That's essentially what a directional light is. It's a light which has essentially infinite distance, so no matter how far away it is from our object, it'll light things up. It has no fall off or anything, which we'll look at. Again, look at what that means in a minute, but you can see we have this, so we have our sphere here, and we have a directional light underneath it. So there's a light directly underneath our sphere pointing up, which is lighting the bottom of our sphere. And then we have two spotlights. We have this spotlight here, which is an orange spotlight. So this will be its RGB quantity. This will be, actually let me just pull up the processing page just so I can make sure I get these in the right order. Right, yeah, so spotlight has, you basically create it with what color you want, so the red, green, and blue. The X coordinate of the light, the Y coordinate of the light, the Z coordinate of the light, so where it is in 3D space, which direction it's pointing to, the angle of the spotlight cone, and the concentration that we'll look at in a minute. But basically, so spotlights are more, I guess, kind of like torches, where you have, so the big, confusing my terminology here, but the big searchlights you have, sort of, you can think of them like having an infinite distance. The spotlights have a fall-off radius as well. So you can see where our directional light is basically lighting up the entire bottom of our sphere here. These spotlights only light up a certain amount. So we can basically say how wide we want them to be, like right down from focused, like a laser, to sort of spreading out quite far. And we can define the colors as well. So yeah, this one we have two spotlights. The one which is making this orange dot here, and the other one which is following my mouse pointer and making the white dot. And yeah, you can see like this sphere is blue. However, when we shine a yellow light on it, it's taking on the characteristics of the light over the characteristics of the sphere. Actually, I think it's blue anyway. Maybe it might even be white. Let's have a look. So I think it's no lights. So you can turn lights on and off. I'll just have to try and remember what the command for it is. Lights. No lights. Okay. Well, that didn't work, did it? Alright, let's just try it. Maybe it's turning them on automatically when I tell it to draw some lights. Okay, there we go. So there's our sphere, and it's actually just a grey sphere, essentially. So there is actually no color associated with the sphere. So you just have this grey sphere floating in space. We have our directional light, which I think I actually got the definition wrong. Yeah, sorry. So I told you wrong. It doesn't. Directional lights don't actually have a space in or position in 3D space. They just have a color and a direction which they're pointing. So you can imagine directional lights are kind of like a light placed infinitely far away from the environment or from whatever you're looking at, but they're infinitely powerful. So essentially, like the sun is for us. So the sun is so far away, we don't even need to sort of really consider it. But, you know, its light hits us regardless. So in the case of lighting in a 3D environment, a directional light, we basically would just say what direction it's pointing, and we don't need, and what color it is, and we don't need to specify anything else. So in this case, we've got our directional light, which is blue. So 51, 102, 126. So we can change that. This will make it more, yellowy or greeny, sorry. So whatever colors we define here, it'll basically shine upwards from this direction. E.
Could we just stop you for a second?
Can we do it after class? It's probably, we've got it set up now, if that's all right.
Okay. All right.
It's balanced on a chair. It's working for the meantime. Cheers. Yeah, so we have our directional light pointing up, shining green. Sorry?
How does that
12. Yeah, so we have a grey sphere, we're shining a light into it, and it's basically pointing up whatever color we specify. Then we have our other spotlight, which is shining yellow in towards it, and then we have the other spotlight, which is moving. And you can see when we add the two of them together, like this one sort of goes more whitey. I think the spotlight is slightly more blue, so there's a slight blue tinge to it. And then when we move it in there, it's sort of, we add the yellow and the whitey bluey color in to get that. So if I just make this, oops. I just make this a little bit. Make this white instead, hopefully that'll be a little clearer. So yeah, now you can see this is our moving spotlight now is white. We can see that the object we're looking at is white as well. We have a greenish coloured light from the bottom. When I move the white spotlight over it, it sort of becomes a mix of this white and green. And then we have this orange as well. And when I move that over, it sort of becomes a mix of white and orange as well, which as you would expect. And you can sort of see a bit of a specular highlight there when the two lights are combined together. It's becoming really bright in that point. So yeah, it's pretty sort of simple to get lights going and processing anyway. You just have to decide what sort of lights you want, a directional light, spotlight, whatever, and then just look at the definitions of them. So directional light in processing, you define a color and then a direction it points, and you just assume that it's out at infinity pointing in that direction. And then spotlights are a little bit more complicated. You need to define their color, their position, their angle, and then some other stuff as well. And the other one as well, which isn't shown in that example, is a point light, which is essentially it's kind of like a directional light, except it doesn't have a direction. So you just specify where it is, and it just lights up like an ordinary light bulb. You say it's here, and it just radiates light in all direction. So there's obviously a few more examples of lights in here, some of which are more interesting than others. So this one basically just shows this example we've seen before. So lights, and then if I click the button, it turns the lights off, so we can see the difference between having that shading and not. This one doesn't even, it just has lights on, which basically sets up a default light in the environment. And I can't remember if any of these other ones So this is directional lights now. So you see two spheres and basically the directional light. So again, this is a directional light out at infinity, and as I move the mouse around, it basically just moves the vector. So you can sort of, when I say it's out at infinity, basically you would just want to draw a line from wherever your object is out through your vector, and it'll be out at infinity in that direction. So it's sort of a little bit weird because we never actually, when this moves around, you sort of think it's changing its position, but it's actually not changing its position at all. You're just changing the direction it's pointing, because the fact that it's out at infinity means that it's kind of wherever. So it's a bit sort of abstract to think about. We just talk about its position, its direction rather than its position. And then I talked about specular highlights before. So here's sort of a specular highlight as well. So we're increasing the specularity of our light source, and you'll notice as it gets brighter and brighter, we sort of get this, it's almost washed out, sort of really bright reflection in the center there, which is kind of more obvious on the screen than it is on the projector. But that's, at the point where the light source is basically in the same space as the camera, and the light's reflecting on it and coming straight back into the camera again. So yeah, point lights are just a light in space. So just imagine your ordinary incandescent bulb. You basically say whereabouts in the room you want it, and it'll light up everything in every direction and what color it is. Directional lights basically sit at infinity. They're like a searchlight, and they just point in whatever direction you define. And then spotlights, you define their position, so whereabouts in the room they are, whereabouts they're pointing to, as well as their angle and concentration. So these ones are a little bit more complicated, but you can do more with them. And in OpenGL and stuff, there are additional light sources, but we're only looking at the processing ones. So I said, you know, the spotlights down here, they have this angle and concentration as well. This is basically what we're talking about. So the angle is the angle of the cone that comes out of them. So the wider the angle, obviously, the wider they'll light up. So in our example before, we saw these ones, and the angle will define how wide that circle that they light up is. And then you have what's known as the intensity or the attenuation factor, which basically defines how quickly it drops off. So if the attenuation factor is, I can't remember which direction it is, I think it's, if it's really small, it shines like a laser, so it falls off really, really quickly, but it's really, really bright in the middle. And if it's really large, or vice versa, I can't remember which way around it goes, it's kind of like a really washed out light bulb where it sort of, you know, gradually fades out over distance, but it isn't particularly intense. So it's the difference between basically shining a laser at something, so it's a very concentrated beam, very tight, versus one which sort of just spreads out quite dynamically. Right, so that's light. Anyone have any questions about light sources or anything? Again, it's a pretty crash course in light sources, but I mean, processing actually makes it a lot easier. Like things like, you know, I talked about the difference between ambient and ambient and diffuse and specular highlights. Processing actually hides a lot of that from you. You can look at things like setting the specular values of lights and so on and so forth if you want, but you can just sort of do directional light, point light, etc., and it'll sort of set up those values to default values, which makes a lot more sense. It sort of just sets the ambient, the diffuse, and the specular to, well, the diffuse and the specular to the same value, and the ambient to 0, so that it reflects more what you would expect a light to do, rather than sort of, you know, what you can do if you want to mess around with things, which you can create lights which wouldn't really exist in the real world, so they have a different specular color than a diffuse color and so forth. But yeah, there's, you know, again, there's plenty of documentation on the processing site which goes into more detail. So looking at specular, light specular and so on, where you can define various specular values. So lights, changing the specular color of materials, changing the specular color of lights and all that sort of stuff. So it's there if you want to access it, but processing sort of, again, hides a lot of it away. So unless you actually want to deal with it, you don't actually really have to worry about it. So we're all happy. So we're just going to look at a few other little graphics things that just to sort of round off this part of processing and software development anyway. So we've looked at creating our own primitives. We've looked at how we can set up cameras, how we can create 3D objects and so on and so forth, how we can light them. What if we want to actually work with images? So let's close all of this. So what if we want to work with images? Sorry. Go into here, topics. We're looking at image processing. What if we want to look at images? Processing provides us this p-image class. So p-image basically is something which allows us to load an image into it, and then we can do some processing over the pixels. So if we want to create a new p-image, we just say p-image and give it a name. And then when we want to load some data into that image, we just use load image, and that will load a file name. So in this case, ystone08.jpg, and then we can like that will return a p-image. Then from there, we can, if we call load pixels, it will load all the pixel data, and we can extract out the pixels and do some stuff with them. So in this example here, this one's not a particularly exciting example. Just see if I can show sketch folder. So this is the image that it's loading, essentially. So it's a picture of Yellowstone, I think. And in this one, in this example, where are we? Here, if we have a look, So our setup stuff's all normal, 640 by 360 window using the 3D class. We have where's width and height defined? So we create a value of an array to store some pixels in, an array to store some values in. We load our image, and then we loop through so we can get a dot height, a dot width will be the height and width of the image that we've loaded, and then we can extract each pixel just by going a dot pixels, and we just reference that like an array. So the array will be width wide by height high, sorry. So basically it'll go 0, 1, 2, 3, 4, 5, 6 up to width, and then it'll start. So say we have a 10 by 10 image, it'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 will be the second row of the image. So if you just imagine breaking it down to pixels, we can reference everything like that. So we can loop through the entire array by basically iterating through each width pixel, and we've got two loops here, one which goes through every pixel in the width and one which goes through everyone in the height. We store those values, and then basically we have, in this one, we get for each value, we create the value array, and we do that by getting the blue intensity of the pixel in that location. So essentially in this one we're creating an extruded 3D map. So you see each of these pixels is sort of like a little line in 3D space, and those lines are computed by how much blue there is for each pixel within that image. So every pixel in here, we extract the blue value, and that defines where it sits in the 3D environment. And then if we look down at our draw method, all we're doing is just using line to draw a line in the 3D environment based on the depth of that blue image. So let's have a look at probably a slightly more easy to understand example. Explode. So this one now we're going to load. So in processing, we always look in the data folder for any data files. So we have a PDE file in one directory, and under the data folder, we say load image, it'll look in the data folder, load it. So this time we're loading this EAMS or EAMS or whatever it is, so this little picture here of some house in the woods. So we load that into our P image called image, and then we figure out how many columns and rows there are, and then for this one we basically go through, calculate its color, and calculate a Z depth based on the brightness of that pixel. So if we run this example now, and this one basically, if we go down and have a look at the draw method, we're looking at the Z value depends on the position of the mouse in the X coordinate of the window, and we multiply that by the brightness. So the brighter an object, or the brighter a pixel is, the further away it's going to move. And now when we start like this, the object is normal, and as we move the mouse further away, all of the pixels sort of move further away from their starting location. So at our very basic thing, we just draw each pixel at a certain depth, one after the other, and then as we move our mouse away, depending on the brightness of the pixel, we push it closer to the user, so we can explode our image quite easily. So yeah, with our P image, we can load an image, or processing allows us to easily load an image, and then using image.pixels, we can get each pixel in the image, and we can do stuff like get its brightness, get its red, green, blue value. We could just draw its color, whatever we want to do. And yeah, again, there's plenty of examples looking at various bits and pieces on what we want to do, edge detection, blending, blurring, etc., etc. Oops, I've opened up the wrong slide. And yeah, we can get, there's two ways of accessing the pixels. So we can do image.pixels, like we saw in this example here. So image.pixels, and basically specify what pixel location. Otherwise, we can also do the same thing by going image.get, and then we specify the X and the Y location, which is potentially a little bit easier to understand than trying to access it as an array, and works in exactly the same function. It might just be a little bit slower. So yeah, in all the examples, they just treat it like an image where, if you have an image, this is pixel 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, along like that. Otherwise, you can just use the get and specify the X and Y locations to get a pixel at that coordinate space, so you can extract various pixels out.
How is the get pixel methods and stuff? Is that only necessary if you want to manipulate the actual pixels? You don't need to just do that, just to load the image into the...
No, so to load the image, all you have to do is just call load image. Yep. Right, so moving from image manipulation, so we can load them, we can get out various pixels and do stuff with them if we want. We can then move on to texture mapping. So obviously, we've looked at how we can create primitives like planes. We've created cylinders. We've created floating cubes, so on and so forth. But if you're just talking about straight out 3D models, 3D primitives floating in space, they don't look particularly impressive. They just sort of are flat shaded, or if we maybe put some texture on them, like shaded by the lights. What's far more interesting and the easiest way to sort of add detail and add interesting things to our models is to actually map a texture to them. So we load in an image, we apply it to the 3D model we've created to make it look a bit more visually stimulating. I mean, essentially it's like just sticking wallpaper on a surface. So this is the sort of thing you can do. You've got this helicopter and you look at it. I mean, this is a bit higher quality than the ones we've been sort of making, but you can imagine this is just made out of like lots of little triangles and stuff like that. If we didn't have any textures on it, it would look quite boring, but you can easily stick some textures on it and it starts to look kind of cool. So in texture mapping, we use a pattern to determine the color of what's known as a fragment or a piece of the model. We can create this pattern procedurally, so we could, actually write some code to basically say, I'll do this part black, this part white, whatever, or we could just load in an image. So here we have a cylinder, so we looked at how we could create cylinders in it last week. And then if we want, we can load in this image of the Coke Classic, and we basically just attach that to the cylinder, and now it looks like a can of Coke sort of thing. So with textures, the way they're usually represented in graphics modeling programs is we map them in what's known as a UV map, so U and V instead of X and Y. Somebody chose to use U and V as the naming of the coordinate systems, and basically that goes from 0, 0 at the one coordinate edge to 1, 1. So when we think about images, usually we think about, this image is 640 pixels wide by 480 pixels high. In texture mapping, it's always 1 to 1. So if we wanted to go halfway down the image, we'd do 0.5, 0.5, 10% of the image would be 0.1, 0.1, so on and so forth. But basically, it's pretty much always going to be the image goes from 0, 0 to 1, 1, regardless of image size. So if we want to texture map it, what we can do, these are, so these are the OpenGL coordinate, OpenGL systems. So in processing, I think it's just text coord. We actually just call texture image, and then when we define our vertex now, our vertices take an additional 2 parameters for where the vertex images should look at, but we'll come back to that in a minute because we have an example on the next slide. But basically, we call our texture function with UV, which specifies whereabouts we want it to start. So, if we're drawing the cylinder, and imagine this is somehow the cylinder is just one fragment, we define it start 0, 0, and at the end 1, 1, or at the far corner 1, 1, and then wrap it round. But usually we make a cylinder out of multiple little segments, so we'd have to figure out at each point around the cylinder how far around the texture we want to map. So if we had, say the cylinder was made by 10 quads, this point might be 0, 0, this would be 0.10, this would be 0.20, 0.30, so on and so forth. And then we just use our texture map that we load with our P image. So this is why we looked at P image before. So load image earth or whatever, and then we basically need to tell processing what texture we want to load at any point in time. So texture, and then we just pass in the P image, and we'll say, okay, we want to start drawing with this one. And then when we create our vertices, exactly like we saw last week when we basically say vertex XYZ, now we say vertex XYZ, and we also say whereabouts we want the texture, the UV coordinate of the texture to come from, so we specify the U and V coordinates there. So we'll start with the textured cube example. Topics, textures, textured cube. So here we have our textured cube like we've seen numerous times before. Well, sorry, our cube like we've seen numerous times before. If we look at the code which has been used to create that, again, you just see, like we saw, it's creating the front face, so -1, -1, 1, -1, and back face, and bottom face, top face, right face, left face. But the only thing different from the examples we saw before is now we have, for each of these, another 2 values at the end, which is the U and V positions. And remember, as I said, it goes from 0 to 1, so 0, 0, 1, 0, 1, 1, 0, 1. And up here, you see in our setup method, we load in this texture Berlin1.jpg, so we could grab any image we wanted. It's going to be difficult. See if we can grab one of these images out. No, it's going to be difficult, right? Okay. Jump to Google then. There we go. Just grab this image, throw it there. Cube. Fair enough. Download.png text cube. Hopefully this will work. And now we have that part of our cube. It looks kind of weird because the texture that I've chosen has alpha blending on it. It wasn't a particularly good example. So we can actually see through parts of the texture. Maybe if we do, what's this one? This one might be a little bit orange. Exciting. There we go, so that one's a little bit more interesting, and actually this one is kind of a nice example, this texture here, because if you look at it, in the corners we have basically the coordinates marked out, so the UV texture positions, so this is coordinate 0, 0, this is 1, 0, this is 1, 1, and this is 0, 1, and now we can actually see when we draw our cube, here are where these textures basically map to. So if we wanted to say do a cube with textures on all different sides, what we could do is basically say text 1, text 2, and let's do text 1, whoops, what was the name of that other one? Berlin -1. Berlin -1. And then when we do this, we might go, right, text 1, and so that texture will be applied to the front face, and we'll just alternate between the two of them. So text 2 goes on the back face, text 1 goes on the bottom face. Actually, we're only going to see half this. Let's do text 1, text 2, text 2, text 1, 1, 2. And now when we draw our cube, oops, should cube, that's hopeless, isn't it? Now hopefully we should see, it's not useful. Text 1, text 2. See if we can make sure we can get at least one of these faces drawn in a different texture. Interesting. Right, so which one was which? Berlin is text 2. Let's just do one of these as text 1, text 1. Interesting. Why is that not updating my textures? Maybe I need to begin shape. Ah, okay, right, I see. So that's a bit of a pain. So I actually need to, it only apparently just picks whatever the last texture was mapped between the begin shape and end shape, it would seem. So I actually need to do this for everyone. End shape, end shape. Begin shape. Right, hopefully that will work now. There we go, that looks better. So yeah, apparently between begin shape and end shape it takes whatever, you only assign a single texture and I'll just apply that to everything in there. So if you want to do something where you have multiple textures on a single object, you need to, between each begin shape, end shape, you need to specify, or you need to rather separate each chunk out into different things. So yeah, now you can imagine we can sort of make a dice or whatever, or if you want to do a more complicated one, yeah, you just assign more textures. Also, so we looked at, you can do 0 to 1 and so on and so forth. What we could do though is we might choose to go 0.5, 0.5. So now one of the sides of this texture will be split. So that one there has been, it's only drawing half the width of it now. So what's that, the left face? If we do the front face, to this will work. There we go. So now we can actually, by doing half of the image on the left face and the other half on the right face, we now have the texture looking like it's sort of wrapping around the corner, when in reality it's actually just drawing half the texture on this face, half the texture on that face. But you can do, this is basically how you can have one texture for an entire model and you just basically grab chunks of it to draw on each different part of the model. And from that, you can then go into slightly more interesting examples. So texturing a cylinder. So if we look at this one now, we're drawing the cylinder exactly like we were last time, but this time we also need to figure out the U and V coordinates. So because like a cylinder has the same height at the top and bottom each time, that's fairly easy. It's going to be 0 and 1, but the U value, so the wrapping around, we have to figure out how far around the cylinder we are at each point, so 10%, 20%, and map that to the U coordinates so that we can end up with something which looks like this. So we have our cylinder now, which maps around, although the end of that cylinder has been cut off. You can see now it's wrapped around it. So at each, if you imagine each of these is a rectangle, so there's like obviously one rectangle across there, and then there'll be like another one to there, another one to there, another one to there, another one to there. At each of these coordinates, we need to figure out how far around the cylinder we are so that when we draw it, the textures are mapped correctly. And from there we can get, even more complicated. right up to, obviously the simplest one will be quad, but we can go right up to a sphere where we have to figure out how far around in the texture we are for each part. But then we can do some quite cool stuff like drawing a globe of the world from a single two-dimensional image just by wrapping it around correctly. So that's this entire sphere has just been textured off this single image. So at each point around the sphere, we figure out how far around the sphere we are and say, okay, let's draw this point or this point in the sphere is this far around the texture and so on. So you can imagine this would, if you split this up into a grid, each of those grid points would align to somewhere on the sphere. And then the calculation for calculating the U and V things, gets pretty complicated. So they're using sine and cosine to basically figure out how far around the sphere we are and where that should map to on the texture, so that it actually maps out round rather than being all sort of weird and messed up. So, makes sense? Yep. So I mean, you can do that with arbitrary complicated polygons. You just sort of say, okay, well, this point maps to this point on the texture and so on and so forth. Obviously, it's a lot easier to do that in a 3D modeling program because they often have quite nice tools for painting and then just load the model in. So we'll look at how to load models in a minute. So if we just to sort of sum up, like 3D objects can be represented a number of ways. So they could be represented as what's known as a point cloud, which is where you have just a series of points sitting in three-dimensional space. So each of these points has a three-dimensional position, but nothing else. You can represent it as a wireframe. So essentially this, you can think of this as a 3D object, but really each of these points has no idea of its relation with all the points surrounding it. So as a person, we can look at that and say, oh, that's a bunny, because we sort of figure out that each of these points is probably related to its nearest neighbor in some way. But computationally, these are just a bunch of arbitrary points in 3D space which mean nothing. Then to get to the next level, you basically want to have a wireframe where each point knows what its neighbors are. So, here, this point has no idea that this point is its neighbor, but here, in order to draw these lines, we have to say, well, this one connects to this point here, and this point here, and this point here, and from that we can draw in a wireframe. And then the next step from that is basically a polygonal mesh. So each point not only knows where its neighbors are, but it knows its normal. So it knows that, here's a face here and all the points connect to it. So for things like a wireframe, we can draw it, but we can't tell what is the inside of the cup, what's the outside of the cup. Any of these sorts of things we can't, like you can see the inside of the cup drawn here, but we couldn't sort of do occlusion because we have no idea that, what side's supposed to be the inside, what side's supposed to be the outside. Polygonal mesh is a bit more complicated again. So as a surface normal, so we can now say, well, this is the outside of the cup. So everything we're drawing here should occlude everything inside it. This is what you need if you want to do like illumination, because you have to have surface normals in order for things to reflect and so on and so forth. So if we wanted to represent a 3D object, like obviously we do a point cloud, but then we can't texture map it because we don't know, or we have no faces, we just have a bunch of points. We can't do texture mapping or lighting with a wireframe because we don't know that there's a surface. It's just like a bunch of theoretically infinitely thin lines connecting all these things. But when we have a polygon, we can say, okay, well, this is like, here's a surface here that we could map a texture to, we could light or whatever else. So in order to do a polygonal mesh like this one down here, we need to know each vertex's position, so where each of these corner or edge points or corner points are in three-dimensional space. We need to have the normal list, so which direction each of their surface normals. So this is what I was saying before about how we have a surface normal which is orthogonal to the planars, so that we can light it correctly. We can make sure that we have the right specular highlights and diffuse lighting and so on. And then we have a face list, which basically defines here are all the faces on it. And when we're getting to this point here, so we can do this really easily in processing whatever else just by writing the code. We just say, here's a 3D point, here's a 3D point. To do this, we can do it for simple things like a cube, or, if you go a little bit more advanced, you can do a cylinder or even a sphere. But once you start talking about more complicated objects, you're better off to go to loading 3D models. So, and this is where things actually start getting interesting and getting away from just drawing everything out of cubes like Minecraft or something. You can actually start creating 3D objects. So we'll look at the Cyto Object Loader, which is a model loader for processing. So again, I've actually finally got access to the Learn environment, so I'll put these slides up so you guys can go to the websites and start downloading stuff and having a play with them. But again, it's like all the other examples. What we do is we just go to, for using Windows, so we go to the My Documents folder, then into Processing, and into Libraries. Oops. And we just unzip this OBJ loader into the folder, into this processing folder. As you can see, I've already done it here, but we might as well do it again. And then once we've done that, we can go into processing, and we can just go tools, or sketch, sorry, import library, and you'll see down here we've got our OBJ loader that we can import and load stuff with. And of course that comes with some examples which come into our contributed libraries. So we have our OBJ loader here, and let's just load up this sample. So you see this is basically how this Cyto object loader works. So we import cyto.objectloader, and then we just have this object, or this class OBJ model, which allows us to load an OBJ file, which you can create OBJ files in most of the main 3D modeling programs like 3D Studio Max or whatever else. Or you can find converters if you want to go onto a website like TurboSquid and download a 3D model. Oftentimes you'll find they come with OBJs anyway, but you can also convert them into OBJ file. Then we just, when we want to load our model, we basically just say model equals new OBJ model. We have to pass in this. So we've seen this before with the Control P5 library and stuff. We basically say this is our processing class so that it can do callbacks and stuff. And then we specify our OBJ file name. So dma.obj is, we go, and again into our data folder, we'll see that we've got this dma.obj file. And then we basically say absolute, so we can, there are various ways, absolute, dynamic and stuff that we can load it. And finally, how we want to represent it, as triangles, as quads, whatever else. Triangles is fairly common because most graphics cards support triangle loading. And obviously if you do a quad, you can only have sort of flat surfaces. If you do a triangle, you can sort of split the surfaces and make them a bit higher resolution. And then you can just do things like model.scale, translate to center, and then in our draw method, model.draw will draw our model. So we just translate and rotate our world however we want it, so we can move the model around, rotate it as we were, and then just call draw, and it will draw our model. Then we can do things like enable textures, disable textures, change it from points to lines to triangles, and so on and so forth. So basically it makes it really easy to load our 3D models. So this one's kind of a boring one, which just has a few things, but you can see we have you know, a sort of a circle with a cylinder with a chunk cut out of it. This line, which is made out of lots of cylinders, a cuboid sort of shape, which has got some notches cut out of it, and a triangle, which has got some notches cut out of as well. And I think that's actually supposed to be like O-MA or something. If I can spin it around correctly. It's actually supposed to spell out a word. But yeah, we can turn textures on and off just by pushing T, which makes it really easy, so we don't have to manually say, okay, here's this texture coordinate. We just load it and it comes with the textures. We can turn strokes on and off so we can see how each of these things are made of triangles. So, you know, for this one here, it's for the triangular A shape, it's quite obvious that it's triangle, triangle, triangle. You look at the M, you know, this is made up of a bunch of weird triangles all over the show, but the 3D modeling program which was used to make it decided that this would be the best way to split this into triangles. What were the other examples we can do? We can do, if we do 1, 2, and 3, so this is the point cloud example we saw before. So this is basically all the vertices, just floating in 3D space. So this is all the vertices which make this up. If I push 2 now, these are the lines which connect all the things up. And then if I do push 3, it basically creates textured triangles. So these can now have triangles which show it. And there's one other one which is in this folder, DMA3. Oops. Which is the same thing, but this one now, for the textures, it actually has alpha blended textures, so you can see now this one's got partially transparent sort of bits and pieces on it. So if we go to something like, let's have a look. I've got OpenScene Graph installed on here. So this one potentially has some slightly more exciting ones, or maybe not. Data. 70 OBJ files. All right, let me just quickly convert one of these to something slightly more interesting. So about Cessna. CSSNA.OSG Cessna.obj. Right, so now hopefully where on earth did that put that? Okay, well that didn't really work as I'd hoped. Tried to convert a file and I'm not actually sure where it's put it. It's alright. So if we go to let's just go to TurboSquid and see if we can grab one off there. Maybe we'll have a break and I'll see if I can get one so we can have a look. But yeah, so those are pretty boring sort of examples, but we can grab lots of different models, and TurboSquid's a good place for going to models. So, and you'll find a lot of the models on here come in OBJ files. It's running quite slowly. So you can buy ones off here if you feel so inclined, but I'm too cheap to do that, so we can go price. Let's look at ones which cost $0. So yeah, you can see here, this one comes in file formats MA, 3ds, Max, OBJ, and FBX. So does this one. This one's a nice one. We're going to have to log in to download this though. Remember. Okay, I'll do that during the break and we'll come back to that. But yeah, so you can download OBJ files and stuff off of websites like TurboSquid and so on, and then display them using that. This is another example showing a little character in there. And finally, just to wrap up the graphics part of the processing stuff, I mentioned way back at the beginning that you can do there's the P3D 3D environment that you can do graphics in processing, and I also mentioned that you can use raw OpenGL if you feel so inclined. So if you want to do that, examples. Where are they? Where was that? Those graphics. So we can actually use raw OpenGL, so doing stuff like using vertex shaders and stuff like that. And it's quite a bit more complicated if you want to do that. So you need to do like begin PGL as begin processing OpenGL, and then you bind stuff and use these PGL dot things like vertex arrays, draw arrays, and so on and so forth. If you want to do low-level GL, which, to be honest, is probably unnecessary for most of the stuff you guys are doing, because the P3D environment actually supports most of these things. But if you find yourself wanting to do like really high-level graphics using vertex shaders and all that sort of stuff, you might want to have a look at it. So here's a basic version, which is using vertex arrays, vertex shaders, fragment shaders to basically draw a rotating triangle. So it's not a particularly interesting example, but you know, this is all happening within OpenGL rather than Processor's P3D window or graphics environment. So yeah, you do get your PGL called PGL.BeginGL will create an OpenGL context that you can render into, and then you can just use PGL whatever to do your OpenGL calls, and then PGL end GL when you're finished, and that will render your scene in OpenGL. So it allows direct access to the OpenGL renderer, so you can do stuff like vertex specification, shader programming, and so on and so forth. But you still need to do stuff through processing, so you can't just do GL vertex 3F or whatever and it'll do it correctly. And there's there's examples in here like GL graphics, which extends the processing OpenGL renderer to support things like textures, post-processing filters, 3D models, and so on and so forth, if you want to have a look at it. But as I said, it's there if you guys sort of come up against a wall, you go as far as you can and say, okay, I need to actually jump into OpenGL because I really need to use vertex shaders or fragment shaders or whatever that the P3D environment doesn't handle, but we're certainly not going to go into it, because if you're sort of hitting that point, whether processing is really the right language and environment for you to be using is kind of debatable. You might be better off going to OpenSceneGraph or something, which we're going to be looking at later on in this course anyway. So it's there if you really love processing, but you've hit a wall as far as what you can do with the P3D environment. Otherwise, we'll take a short break there, and we'll come back, we'll start looking at Arduino so that you can do your assignment. So any questions just in the meantime? Again, I know it's been a real sort of just as fast as we can get through this sort of material, but there's plenty of like examples and resources out there. I'm sort of more here just to show you guys, you know, these are the sort of things which is possible to do, so that then if you're interested in them, you can sort of go and have a look at examples on open processing or whatever else. But yeah, otherwise we'll stop for maybe a 5-minute break there, and then we'll come back after that. Ooh. All right, so I did eventually figure out what password I used to use 10 years ago and get into that site. Unfortunately, the house was kind of too big to work properly, but I got that other one going. So this is that Cessna model that I tried to convert before. So you can see, you know, you can actually do some quite cool stuff, like just by loading 3D models. Obviously, you just have to be wary that you know, the number of polygons and stuff in there. If you have, like that house was 8 megs or something, trying to load that in there, it sort of chugged along kind of slowly, and then it was so enormous that I couldn't actually see anything at the end of it. So yeah, never mind. But yeah, you can actually load in quite nice models and display them, and if you're doing a game, you can do your game in there with 3D models that you've loaded from the environment and so on and so forth. Anyways, that sort of concludes for the meantime anyway the processing. We'll come back later on to look at some sort of more, I guess, advanced or more specialist uses, so things when you want to do stuff like audio, playing video, so on and so forth. We'll come back and we'll look at some of those later on. But for the meantime, we're going to jump ahead now to some hardware prototyping. So we've looked at software prototyping now. Well, I guess you guys started with working with Mark, with looking at how you can sort of do paper prototyping and stuff like that, video sketching. So you started really sort of low fidelity, high level, you know, drawing stuff on pieces of paper or using mock-up tools to mock things up, and then we sort of moved down to a lower level and looked at software prototyping, how you can make like quickly mock up stuff and processing and stuff like that to you know, create these experiences. And now we're sort of going to go a level below again and start looking at hardware prototyping. So say you have this great idea where you basically want to create an RFID reader which is GPS enabled, so you want to be able to go to a store or whatever and read some RFID things and then tag them, or you're in an enormous warehouse and you want to be able to geotag where RFID things are. So I mean, there's basically pieces of technology which exist. So there's GPS devices at the moment. There's these wireless air cards, or you can do stuff with mobile SIMs these days. And then you have RFID readers. So you really want to combine the three of these together to create this product. So you could, go out and buy all the various components. You could build your own breadboard and stuff and wire everything up, and hopefully it'll work. However, obviously that's really hard to make, and the whole idea behind what we're sort of doing here is trying to make things as easy as possible so we can quickly prototype stuff up, see if it works or not, see what needs to be done before we get to this final level. So yeah, this is sort of a rough timeline of how productive you can be with various things. So in software, start off back in the days using punch cards or tapes or whatever, writing things in Assembler or COBOL. It was quite difficult to sort of, you had to put a lot of thought into stuff before you even sat down and started programming, otherwise nothing would happen. As time's gone on, it's become sort of easier. We have these open source libraries we can build on top of, which take care of a lot of work for us. We can use languages like Java and stuff, which are sort of quite easy to sort of, or especially processing these days, which make it easy to get started. So you can sit down and processing, and after a couple of hours, you can sort of have something you can show to someone and say, this is roughly what we want to sort of look at. And, there's even easier things these days. Hardware has been a little bit slower to sort of get easier to use. So, back in the 70s, there was, you'd buy integrated components, or you could buy like analog components, so on and so forth. Over time, you can still get ICs, integrated components and stuff. You can get field programmable gate arrays, which are sort of programmable logic chips these days, which are, a little bit better, but it's definitely been, compared to software, it hasn't had this sort of, real sort of rush to make things easy for people to get going up until really recently. And you sort of have this consumer electronics problem where, you have the scale of economies. So the cost to build stuff, if you're doing a small run of things, so you're only building 100 units, it's pretty expensive to create prototypes. Like we all know that the more things you create, usually the cheaper you can do it. You can, if you're building 10 million units, you can just go to like factories in China and they'll produce them for like, $10 a unit. But if you're only building 100 of them, it might cost you like $100 because you have to do things manually. So you're trying to find the sweet spot in the scale of economies where you can sell enough units that you can build them cheap enough that people actually want to buy them and so forth. And then you have product margins as well. So, when you first start building your device, your cost of production, it's really expensive to get all the manufacturing processes. It's really expensive to do all the R&D and stuff. You're not going to be making a hell of a lot of money to begin with. And it's after, often things like, consumer electronics, it's sort of 2 years. So Sony releases a new line of televisions and they're not actually going to be making much money until sort of 2 years after launch, because the cost to build the panels has come down in price. They've got a large enough manufacturing pipeline now that they can sort of actually start selling things and actually start making money off it. And then you sort of, you hit the sweet spot where after a couple of years you're actually finally starting to make money off your electronics. And then, over time it sort of starts, product margins start coming down, new technologies come out, people don't want to buy older stuff anymore, so you start losing money and then it becomes unprofitable again. And so you sort of end up with these average returns that, you sort of start off getting a bit of return, and then over time, your number of sales decrease. People just don't want your stuff, and over time, the amount of money you're making off of a certain product decreases. So you have to hit the ground. You're trying to do stuff as cheaply as possible to begin with and get as much market penetration as you can early on in order to make any money at all. So innovating in consumer electronics is risky and expensive. If you're not doing these large runs, they're not going to be incredibly popular. You're probably not going to make a huge amount of money. So this is sort of where most consumer electronics sort of are sitting at the moment. So this is basically the number of people who are buying them. So, huge amounts of people are buying these devices. So you're selling cell phones in the hundreds of millions or whatever, MP3 players, LCD TVs, blah, blah, blah. However, there's all these devices down here where not many people are buying them, that there's potential to make a huge amount of money. So, you're talking about vertical markets like healthcare, education stuff where, if you're building a healthcare device, you might sell 10,000 units rather than 10 million or, even less than that. But nobody wants to sort of innovate in here because unless you're selling them for a huge amount of money, you're not going to make a lot of money out of them and nobody's going to want to pay a huge amount of money. So you're sort of stuck in this deadlock where you try and build something, but it's going to cost too much to make. And so no one's going to buy it and you're not going to sell enough. So you can't sell it for cheap enough. And there's this huge untapped market. So today's consumer electronics, you're sort of looking at a market value of about $171 billion a year. However, there's estimates that this long tail where, there's not many devices sold, but, and because there's not a lot of demand, is potentially worth more than that. But nobody wants to tap into it because the potential returns versus cost of investment versus research and the current how processes in consumer electronics just doesn't make it worthwhile. And that's because, currently, and when I say currently, I'm sort of talking up to, the last sort of 5-10 years. It's getting a bit better now, but this is how things would typically go. You'd have your prototyping stage maybe 2-3 times, and then to get to consumer manufacturing, you're looking at 2 to 6 months. So prototyping, piloting, before you move to the like the manufacturing part where you're actually starting to make enough units to get them out into the hands of people and then start selling them. You're looking at spending $40,000 to $100,000 to get to that point to begin with in 2 to 6 months. And then, before you actually reach a production level to the market, so you're making a new GPS device or whatever, you're looking at spending another $500K to $2 million. So you're looking at, over $2 million and a couple of years just to produce your first device. And if you don't have $2 million and you don't have 2 years to get to the market, you're just not going to survive. So it's high cost, high risk, and a long time to market. And building standalone devices isn't enough anymore. So, people don't buy like an Android phone or an iPhone or whatever. They're not really interested solely in the hardware anymore. I mean, you can go out and buy a latest device, but if it doesn't come with good software, it doesn't come with the good user experience and so on and so forth, people aren't going to buy it. Like you could go out and buy the latest and greatest iPhone with all its bells and whistles, but if it wasn't running iOS, people wouldn't use it because it's just hopeless. Things like Android and stuff have made it a bit easier because it's an open source like framework that people can, as long as your hardware runs Android, you can dump it on there so you sort of have it. But these days people want to buy the phone and they want their phone to communicate with their Apple TV and they want their phone to communicate with iTunes. So I can download a song or a TV show on iTunes. I can watch it on my phone, then I can go home and I can play it on my TV. And you have this whole integrated experience where all your devices are communicating with everything else and everything is linked into everything else. And that's what people are really more interested in these days. They're more interested in the experience. You buy your iPhone because it communicates with your iPad and it communicates with your MacBook and it communicates with your Apple TV and everything's communicating with everything. You buy something once on iTunes, you can use it across all your devices and so on and so forth. So you have this physical interface, the digital interface, and the content interface all wrapped into one sort of user experience. There's been like a few hardware prototyping tools which are sort of trying to meet this or like overcome this thing where you have to build your product and you're looking at 2 years before you can actually start testing, getting it out to market. So there's been Bug Labs have produced a few. There's been the Stanford have brought out their D tools, Arduino and things, spin-offs of that like the NetDuino, which are doing it as well. And this is sort of where these things sort of fall on the price versus technological ability sort of thing. So if you're technically minded, you can just start buying ICs, build your own breadboards and plug everything in. So that's, quite advanced to do. You have to have an understanding of electronics in order to do it. However, it's quite cheap. At the other end, you can go out and buy a Lego Mindstorms kit and you can just stick Lego stuff together and then plug in some wires and basically you've got a little robot which goes. But Lego Mindstorm's pretty expensive. And then, you've got things, the whole sort of spectrum on the way through. So yeah, Lego Mindstorm, expensive but user-friendly. It's Lego, everyone plays with Lego, we all know how it works. And then at the other end you have chips and PCBs and stuff, you build everything yourself, which is really cheap. However, we're sort of looking in this course anyway at trying to find the sort of sweet spot in the middle where Arduinos are pretty cheap, so these things are about $30, or they're $30 to $50 New Zealand, and you can do everything you can do with the Lego Mindstorms in it. You can do most of the stuff you can do with the building the circuits yourself, and so it sort of finds that nice spot where it's cheap enough to use, but it's also quite easy as well. So yeah, Lego Mindstorm looking at about €250. I don't know why these are in euros. I probably need to update these to New Zealand dollars. But Arduino, looking at about $30 to $50. And then you can get like the 80 mega, which is actually the chip which Arduino uses, which is €4. So, if you're not worried about all the other bits and pieces, actually, I'll turn the lights back on now. If you're not interested in all the other bits and pieces which are sitting on this board, you can actually buy just this chip here, which does pull off, but I'm probably going to break the pins trying to do so. So that's just the 80 mega chip. This is sorry? There you go, the 328. So this is the 168. This is actually, the one on this one's actually a bit bigger, but or like a bit more memory, I think it is. Yeah. So you can actually pop that out, and the Arduino part is actually just sort of the shield, which it's what's known as, or the board which it sits in, which allows me to plug it into USB. So it's got a USB chip on there, which allows me to communicate with it over USB. It does power regulation. It breaks out a bunch of various ports and stuff that I can do stuff with. So yeah, you could go out and just buy this chip for a few bucks if you want to. If you're nearing the end of your production line and you're happy to wire up the board yourself. But in the meantime, you can buy this. You can do all your prototyping, all your development on this thing, and then at the end of it, you can just use this chip in your final board, and you can actually start producing something for like $10 at the end. But yeah, so we'll have a look at a couple of the other things before we dive more deeply into Arduino, some of the other sort of examples of stuff which is out there. So I don't know if you guys there was a Kickstarter a while ago, this company which wanted to, he's actually an artist, and he was talking about how, we live in such a disposable society, people buy their cell phones, and then when they get old, they just throw them out, and this guy's like, wouldn't it be great to build a modular cell phone so you could, upgrade the battery, you could upgrade the image sensor and so on and so forth. Wasn't actually really that novel an idea, because Bug Labs sort of was doing a similar thing a while ago, but this got a lot of exposure, so I'm sure the people from Bug Labs were kind of hacked off about that already sort of come up with the idea a while ago, but somebody else just got famous for it. But yeah, Bug Labs isn't exactly the same thing. It's not specifically a cell phone, but if you look at it, it's kind of very similar. So you have the base board, or like the motherboard, and then you can plug in various modules, so you can plug in camera modules and everything else. So I founded in 2006. They won best emerging technology at CES and so on and so forth. And it has this full integrated experience we were talking about before. So you have your physical interface, you buy your bug boards, and they just push into each other. They have a connector which allows you to connect the bits and pieces together. Then you do the programming in an IDE on your computer. You upload the code, so you can, you get the images off the camera, and then you push it to the display screen, or you do some image processing or whatever else. And then you have the content interface as well, so you can go to their website, you can download various libraries and whatnot. You can make things that you can upload your, if you have a camera one, you could have it so people could upload stuff to the website. So it has this fully integrated experience. So it was the first modular 100% hot swappable CE device. So you can just pull things off, stick things in, and start calling them. The software and the hardware was open source, so they had all the schematics, the pinouts and stuff, so you can make your own hardware boards to plug in stuff. Communicates via XML, not proprietary APIs, so XML is the extensible markup language, so anyone can modify it, and as long as you fit within the XML standard, like, you'll be able to communicate with these boards. If they support something, they'll use it. If they can't, they won't. And it was designed to be completely hacker friendly, so you could just, these ones are obviously nicely built with their vacuum packed enclosures and stuff, but you could just build a board, and as long as you use the right connector and stuff, you just push it in there and it will be all fine. So these bug modules, which are these parts here, which push into the main board part. There was a whole bunch of ones which were out there: LCDs, touchscreen LCDs, cameras, GPS, motion detectors, audio, Wi-Fi, digital laser projectors, 3G cell phones, Zigbee. So you could build your own cell phone in this if you wanted to. Obviously, it's not as nice as having a fully built, nicely enclosed sort of thing because it's quite a bit bigger. It's got bits and pieces hanging off all various parts, but you could build it if you wanted to, and it's a prototyping device. You're supposed to use it to prototype. So, sorry. Yeah, yeah. So I think that was more inspired. Well, I guess by the guy who started bringing out the cell phone. Yeah, which was probably inspired by this in the first place. But yeah, Google has actually started to sort of build something like this now as well. Slides need to be updated a wee bit, but we're focusing on Arduino in this course anyway, so it doesn't really matter. Then there's the Dragonfly IDE. So, you basically say, okay, here's where all the modules are plugged in and so on and so forth. It's built on Eclipse. I think it used like a Java sort of style language or a C# style language that you could write your code and basically have your modules communicate over XML and so on and so forth. And then you have the content interface. So, you can share libraries that you've written with other people. You can share your designs of various hardware things so people can build them themselves, and you can choose whatever licensing you want. Make it available. So the idea is this was the current approach, and what they were trying to do was change this. So you see here, in the old thing you have your prototype, and then you do your alpha and beta, and you're looking at 100K to get to the consumer manufacturing, so you can put devices in people's hands and have them test out. They wanted to sort of try and change this thing, so you could do your prototype, your pilot, and your alpha testing in a month rather than 2 to 6 months. And then so now we're looking at, instead of taking 2 years to get a product to market, we're looking at 12 months. So with half the time and with half the cost. So we can go right up to actually delivering, because it's nicely enclosed and encapsulated, we can actually deliver our bug platforms to people and have them actually use them and test out the user interface, test out whether we're developing is actually going to be useful to people, and so on and so forth. And these are some of the sort of use cases that people are doing. So, remote healthcare sort of thing. We have a doctor or a nurse go and visit people, then they fill out a form, and then they'd usually have to take it back, and somebody would have to data entry, and somebody would have to put it in the right format for the web, and so on and so forth. So the idea behind this is you'd go out to the thing with your little bug module in your pocket or in your bag or whatever, and you'd have one of these smart pens which can basically read, detect when you're writing and stuff. So you could fill out the form. That would communicate via Bluetooth to your bug platform, and then that would put it into the databases, put it on the web and everything. So, rather sort of cutting people out of the process, rather than need to go back and hand it to someone who then has to read over it, decode what the doctor's written in their chicken scratch handwriting, put it on the web and all that sort of stuff. It's all done automatically. Another example, so you go and visit your mum, and she's pretty technologically useless. She's got some photos she wants to show you, so on and so forth. You could have a bug gateway which has an SD card reader or whatever, and a Bluetooth thing, and then you've got a Bluetooth photo frame. So you go around and see your mum, and you want to show her photos of your trip. So you just take she's got the photo frame at her house already. You take your little bug module, you slide your SD card in, and it automatically just appears on the photo frame. So rather than needing to try and get her computer working or get stuff onto there, you can just take your little bug module along with you. So, this is sort of, it was a higher level. It's probably slightly easier to use than Arduino because you just plug these things into each other, and then you write some code and hopefully it all works. However, it's more expensive. It's a bit potentially less flexible because, it's further along the production line. And if we just want to prototype something really quick and dirty, we probably want to go a level below that. We don't want to have to sort of try and use the connectors that the bug labs people have defined, so on and so forth. Just sort of where Arduino comes in now. So Arduino is a lower level thing. It's using these ATmega or ATmega, I don't know how it's officially pronounced, but basically using these boards, you write code in a C sort of style thing. You upload it via USB. It's got a bunch of these digital and analog pins which you can plug stuff into, and you can start writing code. You can wire up some sensors and devices, and then you can start start your hardware prototyping. You can communicate back with the computer using the USB connector and so on and so forth. So it's basically sort of bridging that gap where it's really, really easy to start prototyping with an Arduino on computer, and then from there you can sort of, as I said, you can buy just the ATmega chips, and then wire it up into a more permanent sort of thing later on. So yeah, the Arduino co-founder Massimo Banzai said physical computing is about prototyping with electronics, turning sensors, actuators, and microcontrollers into materials for designers and artists. So again, we saw in processing it was a language for artists, it was a language for designers. It's designed to sort of encapsulate a lot of stuff that people want to do on a fairly regular basis, maybe hide some of the difficulties, hide some of the challenges initially, and basically make it available to do it. And Arduino was designed with the same sort of thing in mind. It's giving people access to sensors, to actuators, to displays, etc., in a way that's really easy to get up and going. And it involves the design of interactive objects that can communicate with humans using sensors and actuators, controlled by behavior implemented as software running inside a microcontroller. So you write your software in your Arduino IDE, you upload it to your Arduino, and you go. Like your turnaround time to actually build something is however long it takes you to push some wires into here and write some code. So you're looking at maybe starting from start to finish, you might be able to do something in a couple of hours, which is the similar sort of time frame as we're looking at with processing. So we're looking at really fast turnarounds, perhaps not as nice and clean as something like Bug Labs, but you can build something, you can take it to show someone in a couple of hours. You haven't spent a lot of time building it. You're not that attached to the design. If they're like, no, this is useless, you're not like, oh God, I spent days on this. It's sort of like a couple of hours. You can say, okay, what do you like about it? What don't you like about it? Go back to the drawing board. So what is Arduino? It's open source, so it's open source hardware and software. So, this is an official Arduino du Milanove. I'm not 100% sure how that's pronounced. Arduino is sort of originally Italian, so a lot of the board names are in Italian. I'm pretty sure that translates in English to 2004, because this board was released in 2004. This is one which is done by SparkFun Electronics, called the Red Board. This is the one you guys will most likely be using. We have to buy some more of them, but it's done by a different company. It's using, in fact, you can see in this one we've got one of the ATmega chips. This one uses an SMD one, so this is basically doing the same chip, but unfortunately you can't pull this one off. Well, you probably could if you had a very steady hand to desolder it, but you can buy this, make your own things. But yeah, it basically does all the things that this can do, but it's made by a different company. So I can write some code for this and I'll run on that one pretty much the same. I mean, obviously there's a few things, like this one probably has more RAM or more flash memory, whereas this one doesn't. But, more or less the same sort of thing anyway. So they're easy to program. It uses a really simple IDE, which might be familiar to some of you. It uses a simplified version of C, C++, so the Java you've been learning is pretty much the same sort of thing anyway, and it has a simple hardware abstraction API, so rather than needing to know real specifics about how these ATmega chips work or whatever else, you basically just have things like you say digital write 1 and it will put out 5 volts, digital read and it'll read in 0 to 5 volts, analog read 0 to 255 and it'll put out a voltage between 0 and 5 volts and so on and so forth. So it's really easy. You're talking about just switches either being on or not, rather than needing to try and figure out how to turn them on, make sure they're at the right voltage and so on and so forth. And it is an electronic prototyping platform. So, it's there to enable you to do other things. It's not for you to focus on what this board is capable of doing. It's for you to focus on what you want to build, and this board makes it easy to do so. So this is the hardware. So this is a sort of older version. So this is the Arduino Uno, which I think the SparkFun boards are actually based on that specification. But you can see this is actually slightly closer to that, although I think this one has it's the same Arduino board, same ATmega chip, sorry. But yeah, so it's Arduino's a board, so you have a bunch of digital I/O pins, so these can output either 0 or 5 volts. Or you can read in 0 or 5 volts if it's a switch. So output voltage should turn on lights, turn on motors, turn on whatever you want. Or you can read in from switches, you can read in from flex sensors, whatever else. You have your actual microprocessors, the ATmega. You have some power pins, so if you need to power the board or power other devices, you can do it off here. And then you have some analog input pins, so for things like potentiometers, so you can have like little dimmer switches you can turn on and off. You can have flex sensors, you can tell how far something's flexing, so on and so forth. Then you have USB port, which you can use for powering it, reading and writing from it, and a USB to serial converter. So basically you do stuff over serial communication, so all the USB stuff is taken care for you. It's nice and easy, just plug it in and it goes. And then you have typically a power supply as well. So I think some of them only have the USB ports, you just power it over USB, but a lot of them have this, so you can plug it into the wall. You program it once over USB and then you plug it in and it'll continue running your program indefinitely, or people power them over solar power, so they build their own weather stations or plant monitors or whatever, and then they just plug them into a solar panel or a battery and leave them out, and they just do their thing indefinitely pretty much. So yeah, this is sort of the rough idea. So digital pins, you have analog pins, you have power pins, USB, power, you have the reset thing, you have some in-circuit serial programmers and stuff if you don't want to use USB for whatever reason, so on and so forth. But I mean, the main things which we're interested in is the fact that it has USB, power, digital I/O, analog I/O, and a processor. Is pretty much the things that we're going to be working with. Because it's open source hardware and software, there are a million different formats that these things come on depending on what you want to do. So there's things like the standard boards, the Uno and the Du Millenove, which, I mean, you'll be using the SparkFun Red board, which is basically based on this format. This is an older format. Then you have LilyPad, which is more for wearable computing, so it's supposed to look like a pretty little badge that you can then wire in, so you can have, you can wear it and it looks nice, and then you wire it up to, touch sensors in your clothes or whatever, so on and so forth. You have the Nano, which is a smaller board. You have the Mini, which is a smaller board again, so if you want to do stuff which is really small. You have the Explorer, which isn't coincidentally looks kind of like a gamepad, because it is a gamepad, so you can program this to work with various game consoles. You could use it to program with controlling on computers. This one I think has a controller, a little buzzer, it has some buttons, and I think this might be like a touch sensor sort of thing as well. There's numerous boards out there now, like the Arduino official Arduino website, so arduino.cc has a list of some boards out there, but everyone is bringing out their own ones. So the Uno, the Mega, LilyPad, Nanos, Minis, Serials. There's dozens of them out there now, and in fact, if you go to things like, so I get a lot of our one from Nice Gear. It's actually probably .co.nz now that I think about it. So these guys have like lots of Arduino stuff in here as well as other ones. So they have all sorts of different Arduino things, as well as like display modules, LilyPads. They've got various other Arduino spin-offs as well, so DF Robot. There's hundreds of them. I'm not going to bother going through all of them, but it's worth sort of, if you're looking at doing something in specific, having a look at what boards are available, because some of them do different things. For example, I'm doing a project with Science Alive at the moment, and I've just been trying out 3 different Arduino boards because we need to do Bluetooth communication with a tablet. So we have the Blueno, which is a board which has Bluetooth Low Energy built into it. We have the Crowduino, which has what's known as an XB chip on it, so XB header on it. So XB is this tiny little chip you can get, which does wireless communication. Then I've got an XB header, and then we've been using like the SparkFun ones with a Bluetooth shield sort of thing. There's also Arduino variants which use the ADK, so they allow you to communicate with Arduino using Bluetooth or whatever else, and back and forth. But you don't actually need to use any Bluetooth thing. You can communicate with Arduino with Android and stuff as well. There's 32-bit versions out there now as well. So if you want to if you need more processing power, you can do 32-bit stuff. And there's other ones out there as well which aren't Arduino. So there's obviously the Raspberry Pi boards, which are quite popular, which basically run Linux or some derivation of. There's the Intel Galileo ones now, which run Windows essentially. So they're boards sort of about this size, which run Windows or capable of running Windows and various other things as well. Then there's shields for Arduino. So shields are basically, they plug in on the top. I should have actually brought one with me, but they plug into the top of these things. So you can see here, here's a shield and it's got a bunch of pins and its own headers and it slots in that. This one, obviously you can see this one has USB and power, and this shield here provides Ethernet. So now you can plug your Arduino into a network and communicate over network. And this is what it looks like when it's stuck in the top. So now you still have access to all these things. This one also has an SD card, so you can log the SD card if you're putting it out remotely and so on and so forth. And there's tons of shields for all different things, so controlling motors. If you want to build your own 3D printer, a lot of people do that with Arduino and use these things to control the motors on them. Micro SD, touch screens, input, MP3, so if you want to make your own MP3 player, you can do that with Arduino. Smart meter, so you can measure your home's power usage and so on and so forth. Ethernet, Wi-Fi, RFID, Bluetooth, GPRS, Wi-Fi, GPS, XB, RF stuff. And beyond that, you can plug in all sorts of different sensors and devices and stuff as well. And you find a lot of devices have libraries written specifically for integrating them with Arduino. So you can plug in all sorts of bits and pieces. You can do buzzers, vibrators, relays, LED matrix OLEDs, LCDs, photocells, color sensors, rotation sensors, water sensors, sound sensors, joystick, temperature, humidity, IR, passive infrared, accelerometers, compass, ultrasonic, AC current, hall sensor, CO2, flame, flex, infrared, IR, thermometers, smoke detectors, pressures, pH, real-time clocks, polar heart rate, etc., etc., etc. So, and like as I said, a lot of these come with Arduino libraries. Like people have already ported them to run on Arduino, and they just like plug this device into digital pins 1 and 2, upload this code, and now you can and they'll have a library. So it's like instead of needing to try and figure out what all the things are, you'll call a function like check temperature, and it'll return to you a number which is the temperature in degrees Celsius or whatever else. So people have written the code to translate the numbers and the data you're getting back from these sensors into stuff that you can just use in your thing, which is really nice. Like I bought, in fact, a little board which had an old Nokia LCD screen on it, and you plug that into there, and somebody had written code so that you could write text on there. So you just write print to screen, and then you write some text and it'll appear on the screen, or you could like print or draw a bitmap and it'll draw a bitmap on there. You can control individual things, and you're like talking about one line of code to basically have recreate the Nokia old LCD screen. So you could write your own Nokia Snake game, or combine it with a GPS or like a GSM module to make your own cell phone running off Arduino if you feel so inclined. But yeah, so there's lots of stuff in there. There's the Android ADK, which allows you to communicate with Android phones. Obviously, the advantage being that your phone already has a number of sensors in it. It's got a camera, a compass, light sensor, G sensor, vibration, proximity sensors, blah, blah, blah. You can actually send data from your phone to your Android device and so on and so forth. So if you wanted to do like something really complicated, you buy a cheap, crappy old Android phone, pair it with Bluetooth with your device, and then all of a sudden you can access all that data and do whatever you want with it. Like people do stuff with high altitude balloons. So they buy huge big balloons, fill them full of helium gas, send them up into the stratosphere with an Arduino and a cell phone. The cell phone handles all the GPS and stuff, and then the Arduino has a bunch of sensors plugged into it so they can measure air temperature and all this sort of stuff. So you can do a lot of really cool things with this, really. And I know it's cheesy and whatever, but the limit really is sort of your imagination as far as how far you can push it. And yeah, we'll stop there. We'll look at some Arduino software on Wednesday, and then we'll start looking at it, and hopefully by then we can have some kits that you guys can take home and start having a play with as well. Cool. And if anyone has any questions, fire away. Otherwise, yeah, we'll try and learn this afternoon, and hopefully we'll have your assignment, which you'll be doing over the next couple of weeks.